Alright, so let's come back, and then we will discuss the intrinsic semiconductor in more details. So intrinsic here means no doping. It's pure silicon, for example. If it's pure silicon, then we will argue that the Fermi level is in the middle of the band gap. So it's exactly half of the band gap. So why is that? Because if it's intrinsic semiconductor, as you know, the only way you create electron and hole is by the thermal energy. So once you create one electron in the conduction band, you will create one hole in the valence band. So the probability to find the electron is the same as the probability to find the hole in the conduction band. So the Fermi level is a reference level, so it must be in the middle. So this Fermi level is a reference level. So the probability to find the electron and the probability to find the hole will be exactly the same. This is because it's intrinsic. Okay, then the next question is, what is the intrinsic carrier density, Ni? So here, this is with some finite temperature, as we discussed. So the electron and hole may be generated due to the thermal energy. But then the thermal energy here, for example, you have kT. So with this kT thermal energy, what is the density for the electron and hole? So in this case, because it's one-to-one mapping, so we use this Ni to represent the intrinsic carrier density. And you know it will be the same for electron and hole. So in the intrinsic case, Ni equals to N equals to P. And here carrier means either electron or hole, because they are equal in terms of the density. So then how can we get this Ni? Any idea? Well, if we want to calculate what is Ni, so we can start from those two equations. This is how we get the electron density in the silicon, given the temperature, and the equation for the hole density, given the temperature. So what we can do is to, let's say, do the NP product here. If you, let's say, use N times P, then what you can do is to do those multiplication of those two equations. MV exponential EV minus EF over KT. Right, so this is what you have, and then you can rewrite this NC NV together, and then the exponential term, you can combine those two exponential terms, and then plus EV minus EF over KT. So here you see that EF minus EF, so those two cancel. So what is left is this EV minus EC. So what is EV minus EC? Or let's say negative EC minus EV. So we put the negative sign out. It's the same thing. So the reason here we have the EC minus EV like this is to create this with a band gap EG is EC minus EV. So this is a band gap. EG over KT. And you know for the intrinsic case, N equals to P. So this will be Ni squared. Because N is the same as P, is the same as Ni. So it's Ni squared, like this. So if you take the square root, you get Ni. If you take a square root, you know, for the exponential functions, square root means divided by 2kt. It's, you know, this is simple math. Square root on the exponential function is like in here, you divide by 2. So here you will get all the physical constants, because NC, NV are the numbers we have here, NC, NV. Those are the physical constants. And then Eg is also a constant. For the silicon is 1.1 electron volt. And Kt depends on your temperature. So if you do that at room temperature, you can plug in the T equals to 300 Kelvin, which is the room temperature, like 27 degrees Celsius. Then if you do that, plug in all the numbers, you will get Ni, and this Ni is about 10 to power 10 centimeter per centimeter cube. This is what we have shown you before. That's why in the intrinsic silicon, if you have room temperature, then the electron or the hole density is the same, and the number is 10 to power 10, and we call this intrinsic carrier density Ni. Any questions on this derivation? Can we just use any of the equations? So for this NP product, you have to use both equations and then do the product. What does K stand for? K is Boltzmann constant. It's the constant. And this is just to convert the units from the temperature to the energy. So the coefficient is K. K is named as Boltzmann constant. It's the same Boltzmann here. There is a Boltzmann. It's Boltzmann constant. So it's a way to convert the units. Let's say if you have a temperature in Kelvin, and then if you multiply by the K, then you get the energy units, electron volts, and you can convert electron volt to the energy units, joule. So this is just a coefficient. It's a constant. Any other questions? All right, so then this is the derivation, and I just clean up this, and then you can have this in this box, the final equation for the Ni. So here, if you look at the Ni, it has nothing to do with the Fermi level. There's no EF in the Ni. And in other words, if you look at the NP product, it also has no information on the EF. So that means what? So here, those are all physical constants, NC, NV, and Eg. Of course, Kt depends on the temperature. At a given temperature, the NP product is a constant. Or this equation always holds. NP equals to Ni squared. This is always true, no matter it's doping or low doping. Then you can use this to solve this question. What is the hole concentration in N-type semiconductor with 10 to the power 15 per centimeter cubed of donors? So this is no longer intrinsic. This is with doping, and it's N-type doping because it's donor. So N-type doping with Nd 10 to the power 15. Then the question is to get the D, the hole density. So this is N-type semiconductor. And N-type, with donors, this density. So the N will be the same as ND. Why is that? Because as you recall, we said that one donor, let's say the group 5 element, like the phosphorus, will give you 1 electron in the silicon. Because it has 5 electrons, and you only need 4 to form those 4 bonds. So it gives 1 more electron. So one donor, 1 electron. So here the electron density will be the same as the donor density, 10 to the power 15. So here you see that this N-type semiconductor, the N is 10 to the power 15. How about the P in the N-type semiconductor? So you can always use this NP product because it's a constant. And then P will be Ni squared divided by N. So Ni squared, Ni, as we say earlier, is 10 to the power 10. And squared will be 10 to the power 20. And then 10 to the power 20 divided by this N, 10 to the power 15. You will get 20 minus 15 is 5. 10 to the power 5 for the P. So you can see that in this N-type semiconductor, electron N is much higher than the hole density P. Or in other words, the electron is the majority carrier and the hole is a minority carrier. So this is a majority and this is a minority. You can always use this Ni squared divided by N to get P, or divided by P to get N. And a simple trick for you is very easy to remember this. Because Ni squared will always be 10 to the power 20, so it's 20, okay? If the N is 15, then the other one will be 20 minus 15, 5, okay? So if you only look at the exponent here, the N and P, let's say 15 plus 5, will always be 20. If you change the doping density, for example, here if you change to 16, then the whole density will be 10 to the power 4, because 16 plus 4 is 20. So the sum of those two on the exponent is always 20. So you can use this as a simple rule to quickly estimate the electron hole density. Any questions? Can you explain why N is equals to ND? Oh, we just explained, right? So one donor give you 1 electron. Because one donor, let's say group 5, phosphorus, you have 5 electrons. 4 of them bond with other silicon. You get 1 more additional free electron. So one donor give you 1 free electron. Can you repeat what NC, NV represents? Oh, those are the physical constants. So it's called effective density of states. So NC is the effective density of states in the conduction band, and NV is called effective density of states of the valence band. So the effective density of states, you can think that is the maximum capacity you can have at the band edge. For example, for the EC, so that is the maximum number of seats available in that classroom. You can think this that way. And this is a physical constant for the silicon, is this number. Or for simplicity in this class, we assume 10 to the power 19. So it's just the number of available states. Okay. Can you explain what are majority and minority one more time? Majority means you have more, right? Majority by definition means more. So in this particular case, you have more electrons than hole, right? Electron is 10 to the power 15, hole is 10 to the power 5. Then electron is majority, hole is minority. So it's just in terms of the number. Any other questions? . Alright, so then let's look at the extrinsic semiconductor. That means with doping. So here with n-type doping, we will say that the EF is closer to the EC. And why is that? So in the n-type doping, we just look at that example. Electron is majority. You have more electrons, right? You have more electrons. So then, if you think about the Fermi function, right? So then this tail will be higher here than here if the EF is close to the EC. So you will, if EF is close to the EC, you have more probability to find the electrons here. So that's why the electron density is high. Because in n-type semiconductor, then electron is majority. You dope the silicon with donors, so you get more electrons. So the EF is closer to EC. That's the conclusion. And on the other hand, for the p-type doping, if you have the acceptor Na, then the EF is closer to the EV. So these two just opposite to each other. So the conclusion is with p-type doping, EF is closer to the valence band, and you have more holes than the electrons. And again, in the intrinsic semiconductor, then the EF is in the middle. It's a reference, right? So basically, the EF is a reference. Then if you have more electrons, EF closer to the EC. If you have more holes, EF closer to the EV. So that's the conclusion here. Very important. And next, we can look at one concrete example to find the EF if the silicon you have this kind of p-type doping. So the Na acceptor, this is p-type doping. This is p-type. So if you have p-type doping, like Na equals to 10 to the power 17 per centimeter cube, then where is the EF? So this is a typical question for your homework, and also I can guarantee you in the exam. So how do we do this kind of problem? So here eventually you need to draw the band diagram. What you need to draw eventually is to draw this. EC, EV, this is a band diagram. And then here the question is where is the EF? So you need to locate the EF somewhere in the middle. And then here we need to calculate the exact distance. The EF between EF and EC, or EF between EV, we need to calculate here. So for the silicon, the band gap Eg is a physical constant, and we say it's 1.1 electron volt. So here we are always going to use electron volt to represent the distance, because electron volt is a unit for energy, and here we are talking about the energy levels. So this is 1.1 eV, but then now the question is, what is the EV here? So first of all, this EF in this case will be closer to EV, like I sketched here. Why is that? Because this is a p-type, as we said in the previous slide. P-type, then EF is closer to the EV. Then how to get the exact number here? So we can start with the equation. This equation, very important, those two equations. But since this is a p-type semiconductor, then we use this p equation here. Right, so you should start with this one. Sorry. And the exponential. Oops. Let's say EV minus EF over KT. So this p-type, so as we discussed, p-type, the density for hole is the same as NA because each acceptor gives you one hole. This is the same as each donor gives you one electron. So P is the same as this 10 to the power 17. Then you can back calculate what is the distance. Here the EV minus EF is the distance here. So you should back calculate this one because you know the P here, NV is a physical constant, and KT, we should ask this question at room temperature. So room temperature is this electron volts. KT is this number. This is the physical constant. If you use Boltzmann constant times 300 Kelvin in temperature, you get 0.026 electron volts. This is a constant for the room temperature. So then you should back calculate what is EV minus EF. So what you need to do is to move the NV to the other side. Over KT. So what you can do is take the natural log on both sides. Then it's EV minus EF over KT. We can move the terms around. So EV minus EF. Oops. You move the KT to the other side. It's KTO P minus NV. So you see, this is just back calculate here from the equation. So you can plug in all the numbers. The KT is this 0.026 EV. And then natural log P is this 10 to 17. NV is this 10 to 19. Those are given. So you just calculate this, and this carries the unit EV. So if you do that, then you get the number. I will show you that. You need a calculator. So I just show you this one, right? It's 0.026. It's the same here. So I just show you the answer here. So if you do that, then this will be a negative 0.12 EV because EF is lower than EF. So here this distance is this 0.12 because EV minus EF will give you a negative sign. But the distance, if you think the absolute value, will be this 0.12 EV. So with this one, you can label all other distance. If this one is 0.12 EV, then to the EC is about 1 EV, because in total is 1.1, or in this particular case, if you want to be more accurate, is 1.12 EV. This is a physical constant for the EG. So if you have this one, then we know the other distance here. And sometimes we define the intrinsic level in the middle. So this EI is the EF in the intrinsic silicon. So it's in the middle. So if you take half of that, then half of that will be 0.56. So you can get the distance here from the 0.56 minus this 0.12, then you got this 0.44. So here just labeling the distance. If you get one of that, you can label all the others. So you are expected to draw this kind of Venn diagram in your homework. And then the second question, what is the N? So this is a p-type semiconductor, and we know the P is 10 to the power 17. And then we ask for what is the N. Then we can use this NP product. This is a similar example as before. Because N times P will always be this Ni squared. And as we discussed earlier, so you can always use 20 to minus the 17. So you can get 10 to the power 3 for the electron density. So any questions here? This is a typical question in your homework and also in the exam. So the question typically is ask you to draw this kind of Venn diagram giving some doping density. And in this case, is a p-type doping with this kind of 10 to the power 17 doping density. And we can practice again. And I'll give you like 1 or 2 minutes, and you can do it by yourself. So the question is finding the Fermi level in silicon. And the question is at room temperature, that is 300 Kelvin, with this N 10 to the power 17. So this is the first question. You can do it. I'll give you like 1 minute. So eventually you need to have this. You need to draw this EC, EV, and then label where is the EF. So in this case, EF is probably close to the EC because this is N-type doping with this N density. And the question is, what is the EV here, electron volts? So in total, this is 1.1. Okay, so I will give you 1 minute. If you have calculator, you can calculate it. I will watch for any answers in the chat. And also got one question from the chat. Can we assume that the density given to us in the question is either P or N? So typically in the question, it may not directly give you N like this. It may just give you the doping density. So it may give you, for example, ND, the doping density, 10 to the power 17. But if it's a ND, that is donor. Donor is, N-type doping. And you will immediately get the doping density N equals, the electron density N equals to the doping density ND. And then you can start from there. So any numbers for this electron volts? Anyone want to volunteer to give a number? You may need a calculator. So in this course, I think you need a calculator. But since we are virtual, so you can use your computer and so on. But if it's in the real classroom settings for the exam, then you need the real calculator. Okay, I think you should expect a similar number as this case, because this is P is 10 to the power 17. Now is N is 10 to the power 17. So the numbers should be similar here. So let's do that. So this is what we want to get, this distance between EC and EV. And then we get this equation from, you can start with original equation for the electron density. So this is the original equation for the electron density, and then you back calculate what is the EF minus EC. So then you back calculate, plug in the numbers for the NC and N. And here I think in this example, it uses the real value for the NC. But if we use this approximate value, 10 to the power 19, then you will get this 0.12. Or if you use this 2.8 times 10 to the 19, you will get this 0.146. But in the class, I think to make this simple, we will assume this simple number, 10 to the power 19. So then you will get this distance about 0.12 electron volts. And similarly, if the question asks for if the P is 10 to the power 14, then what is the distance of the EF? Let's say the EF to the EV, because in this case, P is p-type doping. So you should use the P equation. Then you back calculate what is the EF minus EV. Then you get 0.3, around 0.3 here. So again, those two examples, you see that if it's N-type doping here, the EF indeed is closer to the EC, and if it's P-type doping, then it's closer to the EV. This respect is corresponding to those two numbers, this energy diagram. Any questions? Yeah, it's negative 0.12 electron volts. So I think that's the typical question you will see in the homework, and hopefully you know how to calculate this. Any questions before we end today? If not, then we will stop here today.